Thanks, Mattia, for joining. I'm very pleased to introduce Mattia Cafasso from the University of Angers, and he will tell us about integrability of Integro-Differential Painlevé equations.
Thank you. Thank you, Antonio, and thanks to all the organizers for this invitation to speak here. So as the title says, I will speak about some integral differential equations that generalize the Painlevé-2 equations, and about applications to the Cavdara-Parisi-Zhang equation, which is a stochastic PDEs. So I will start with the plan of the seminar. So I will tell you what is the main character of this talk. So a sort of generalization of the Tracy-Widom distribution, the one appearing in the theory of random matrices. And then I will explain to you that there are three different Riemann-Hilbert approaches to study this integral differential Painlevé equation. And if I will have time, I will for sure speak about a first approach that we used with Giulio Ruzza and Tom Claeys, and which is described in these two papers here. And if I have time, I will speak about something which is newer, which is an approach that we use with Thomas Botten and Sofia Taricone, in which the main novelty is that we use Riemann-Hilbert problems and Lax pair, which are operator valid. Okay, so a little bit different from what we are used to see. So I will start immediately with the definition of the function that we want to study. And it is constructed as follows. So you start defining a kernel, so a function of two variables, lambda, mu, as this integral, this weighted integral of two IV functions computed at lambda plus r and mu plus r, then integrate over r, over the whole real line with a weight, the weight sigma, which is given by the Fermi factor. Okay, it's given by the Fermi factor multiplied by a certain coefficient that we call here t power 1/3. Okay, so this is a kernel. So you can think about this object as a kernel of an operator, and this operator is trace class. You can easily prove it. So it makes sense to compute the freedom determinant associated to the identity operator minus the operator associated to KAIT, restricted to the interval minus S infinity. Okay. So here you have the definition of the freedom determinant at what is called the freedom series of the kernel. And this function then depends on two variables. One variable is S, which is the endpoint of the interval, and the other one is this T here. Okay, let's see what this T does. When T becomes very, very big, this Fermi factor that is here, it becomes the indicator function of the interval 0 to infinity. Okay, and then in this case, this kernel becomes the classical IV kernel that you find in the theory of random matrices, and this QS t equal to infinity becomes the classical Tracy-Widom distribution for GUE, for the Gaussian unitary ensemble. So what we are studying is really a sort of deformation of the Tracy-Widom distribution. And this object, which is a probability distribution for any fixed t in function of S, has many applications. It appeared already in 2007 in some paper by Johansson on some deformed GUE matrix models. And then in 2010, it appeared, and I will speak a little bit more about that, in relation with the Cavdara-Parisi-Zhang equation. And more recently, in some model of Dean, Ledussal, Majumdar, and Scher, which are model of fermionic systems at finite temperature. So when you study this QST in terms of fermionic system, this parameter T is the inverse of the temperature. And these fermionic systems at temperature T equal to 0, they are essentially equivalent to GUE, to matrix models. But then when turn off the temperature, you get some deformation of random matrices, and these deformations are governed by this function QST. And more recently, there are also some articles in which you study some discrete random processes related to Young diagram, so periodic show processes, and in some limit you see appearing the same kind of equation. But I want to speak a little bit more about application in KPZ, because probably this is what is most interesting nowadays for applications. So the Kadar-Parisi-Zhang equation is this equation that you find here, which is a PDE, which is stochastic. Why is it stochastic? Well, because this is random terms. Technically, this is a space-time white noise. So what does this equation describe? It describes the evolution of a certain interface, which is one-dimensional, so X is the space, in function of T. And it has been introduced by Kadar-Parisi-Zhang in 1986. And the idea is that this is a sort of universal model to describe some stochastic growth phenomena with three main features that corresponds to these three factors that you have here. You have some smoothing that is given by this term. Then you have some nonlinearity, so slope-dependent growth speed that is given by this term. And then you have some random kick that is given by this space-time uncorrelated noise. Okay. And well, the equation has been introduced in 1986. And what is very interesting is that the corresponding solutions, which are distribution, has been observed recently in experiments, like in this article in 2018 by Takeuchi-san. And if I can switch screen for a moment, I want to show you an animation which is done by Patrick Ferrari, a colleague, and gives you a little bit an idea of what kind of phenomena we are studying. So here in this, do you see my screen? Okay.
Yes, we do.
Okay. So in this picture here, you see you have some particles in the bottom. There are these blue particles. And when I press start, in some with some random loose that I don't want to describe precisely, these particles becomes shifting to the right. Okay, so you have the way in which they go to the right is called TASEP, totally asymmetric exclusion process. So what happens is that each particle has an exponential time, a random variable inside, and when this random clock goes on, the particle wants to jump on the right, and the particle can do it just if there is space. Okay, and that's the reason why it's called exclusion process. Okay, because you cannot have two particles sit in the same position. So you have these dynamics of particles, and you associate to these dynamics a certain graph that you construct in this way. If you have a particle here, you put a segment that goes down. If you have a hole, like here, you put a segment that goes up, and so on and so forth. So here you have many particles, so you have something that is going down, this blue line, and it goes up, and down. And at the end, since here you don't have any particles, it goes up indefinitely. Okay, now I start again and I zoom off in this way. And what you see is a random surface that is growing. Okay, this KPZ equation, well, I'm a little bit cheating because you need to consider a little more complicated phenomena, but essentially this KPZ, it describes the growth of this kind of surfaces. Okay, so you have a macroscopic behavior that is given by this red line, and then you have some stochastic oscillations. Okay, and KPZ describes this stochastic oscillation, essentially. Okay, I will stop sharing this animation, and I will go back to the presentation. Okay. And okay, this is a little bit the physical idea, but the reality is that it's quite difficult to understand in a rigorous mathematical way what it happens being a solution of the Kaldor-Parisi-Zhang equation. You need this theory introduced by Heyer very recently. And the reason why this is hard is because you have these nonlinear terms, and then you have problem of regularity when you define the solution. But for some specific solution, there is a way out. There is a more easier way to describe solution. So what you have to do is the following. If you formally define a new variable z with this relation, so this is a Kohlhoff transformation, at least from a formal point of view, you can prove that if H satisfies KPZ, then Z satisfies the stochastic heat equation, okay, which is this equation here, in which you have the classical heat equation plus this term here, which gives the randomness of the equation. And actually, it turns out that this is more easy to treat in the realm of stochastic PDEs because you don't have the nonlinear term. And in 2010, Amir, Kovin, and Castelli, in a really groundbreaking paper, proved the following result. Consider what nowadays is called the narrow wedge solution of the KPZ equation, which is defined by the Kohlhoff transformation, where Z now is the solution of the stochastic heat equation with this very simple initial data. Okay. And then it turns out that this quantity here, that looks complicated, but now I will take some time to explain what it is. Well, this quantity here, which is the exponential of some random variables of which you take the expectation, this is equal to the Fredholm determinant that I defined before. Okay, and if you look a little bit at this expression that you have here, you have your solution of the Kaldor-Parisi-Zhang equation h to tx, and then you have this term which is minus x squared over 4t plus t over 12. So basically here you have a sort of parabola that becomes wider and wider and moves with the time. It's exactly the red parabola that I showed you before. Okay, and when you put this s times t power 1/3, what we are doing is that we are studying really the random fluctuation that you saw before in the picture. Okay, and it turns out that this quantity QST gives you a lot of information. Well, almost they gives you all the needed information about the solution of the Kaldor-Parisi-Zhang equation. Okay, and the importance of the article by Amir, Kovin, and Castel was that this was really the first article in which they gave a precise definition of the distribution associated to a particular solution of the Kaldor-Parisi-Zhang equation. And among the many results that you have in this article, you have this one, which is interesting for a person interested in Painlevé equation, which tells you that the quantity QST, well, up to a sign change on S, is given by a very explicit integral, which is this integral here, which depends on the Fermi factor and on a certain function U, depending on two variables. And this function U, S lambda, satisfies this boundary value problem, which is here. Okay, so this US lambda, pointwise in lambda, as asymptotics for S going to plus infinity as the IV function, and satisfies these integro-differential equations that might look complicated at the first sight, but remember what we said before. Here we have the Fermi factor, the derivative of the Fermi factor. So if t goes to plus infinity, these sigma primes become just a Dirac delta function. And if you look at these equations, this is exactly the Painlevé-2 equation. Okay, and so it is just legitimate to say that this is an integro-differential version, a sort of deformation of Painlevé-2 equation. But now you don't have anymore an ODE, you have an integral differential equation. Okay. So this is what Amir Kovin and Castel found in 2010. And then the natural question is, why do you have this generalization of Painlevé equation in this setting? And the idea is that hidden behind this theory, and actually hidden behind the freedom determinant representation of this function QST, you have the theory of integrable kernels of its isogen Kolepin's love. Okay, if you never heard before about this theory, I will just give you some basic information, which are the following. Suppose that you have a contour sigma in the complex plane, and you have a certain operator k from L2 sigma to itself with this kernel, with a kernel depending on the function on the variable xy given by f transpose x hy, where f and h are vectors, divided by x minus y. Okay, when you have operator of this type, you say that your operator have an integrable kernel according to the definition of its isogen Kolepin's-Lyapunov, and it turns out that if existing, you can compute the resolvent of the operator solving a certain Riemann-Hilbert problems, whose jump matrix is given by the same vectors f and h. Before you were doing f transpose times h, and you're getting a scalar, but you can do f times h transpose and you get a matrix. And this matrix defines the jumps of your Riemann-Hilbert problems on sigma. Okay. This is a general theory that has been used since the 80s, I would say. And what happens here in our in the case that we're interested in is that the kernel that we are studying, so this KAIT, can be rewritten in this form. Okay, so this form is almost the same that I showed to you before, in the sense that you can construct two vectors out of every function in such a way that this is a scalar product of two vectors. But then additionally, you also have an integral, a weighted integral with sigma prime. Okay, so in a way, this is a sort of infinite dimensional version of an integrable kernel. Okay, and indeed, Amir Kovin and Castel, they used a sort of generalization of the Tracy-Widom procedure to obtain the integro-differential Painlevé equation that I showed to you before. Okay, and then Thomas Botner, very recently in 2020, Thomas Botner is a former student of Alexander Ritz. He found a first operator-valued Lax pair for this equation. And how did he find it? Well, he found it using a Riemann-Hilbert problem on the interval 0 to infinity, which is operator-valued. Okay, I will not speak about this because this is not my work, but it was our first source of inspiration. Okay, via the article of Thomas Botner, we had the feeling that something could be done with Riemann-Hilbert problems for the study of this function QST. Okay, and actually, and so now I will describe the first approach that I developed with Tom Claes and Julia Ruzza. What we used is something that was known but not used, and I don't know why, which is the following. It's true that this QST, as I defined before, is the determinant of an infinite dimensional integrable operator. But what you can do using some very elementary manipulation of freedom determinants, what you can do is to rewrite this determinant as the determinant of another operator, which has a simpler kernel. Okay, the kernel that we have here is KAI, which depends on the function sigma on S and T, and it is much easier. It's this kernel that I give here because it's just a classical IV kernel, which we know that is integrable in the classical sense, finite dimensional integrable. And then you have just to multiply this kernel on the left and on the right for the square root of this sigma function shifted by S. Okay, I recall that the function Q depends on S and T. Okay, and here the reason why this form is very nice is because, well, it's a finite dimensional integrable kernel, and the dependence on S and T is not inside this IV function, it's just inside this sigma function. So it's much more easier to be treated. And the remark is that this kernel, as I said before, can be written as F transpose times H divided by lambda minus mu, where F and H are given explicitly by these two terms. Okay. Which means that using the classical theory developed by Syzygian, Kolepin, and Slavnov, you can associate to this freedom determinant here a Riemann-Hilbert problems that now is of size 2 by 2, so quite simple. And the jumps of these Riemann-Hilbert problems are given by this expression here. Okay. I'm not now giving you this first Riemann-Hilbert problem. I'm just telling you that then you have this Riemann-Hilbert problem, you do some manipulation using a function, you do this change of variable that now will be clear, I guess. Instead of S and big T, you use small x and small t defined in this way. And you prove that the log derivative of your function Q is given as this integral here, which depends on certain function psi, and psi is the solution of a Riemann-Hilbert problem that is written here. So you have a certain jump on the real line, which does not depend anymore on x and t, but it does depend on sigma. Okay, and you have a certain asymptotic condition at infinity. The asymptotic condition that you have at infinity is this one. Okay, you have identity plus lower order terms in terms of z minus 1. Then you have this z power sigma 3 over 4, sigma 3 the Pauli matrix. You have a constant matrix A, and then the important stuff is this one, is this exponential here. Okay, if you give these Riemann-Hilbert problems to someone that is studying KDV, that studied KDV, studying inverse scattering theory for KDV, of course they will immediately tell you, well, but this is KDV. Okay, of course we don't have exactly scattering data. We have something that is more generalized, but the asymptotic at infinity suggests that behind this stuff you have KDV. Okay, and indeed this is the case. And the main theorem that we proved, well, the first main theorem that we proved with Tom Claes and Giulio Luzza is the following. You take your function Q, you take double log derivative with respect to the variable x, you add, I'm sorry for this stuff that keep on appearing. Okay, you add the quantity x divided by 2t, which is, by the way, a solution of KDV. And then you have that V defined in this way solves the KDV equation. Okay, so indeed you have, in a certain sense, that this Q is a sort of tau function for KDV. And moreover, and this is also what is interesting, you have this curious relation between V and phi, where phi solved the Schrödinger equation with potential V. So KDV theory is isospectral deformation of this Schrödinger equation, and it turns out that it exists an eigen function phi, such that the potential can be written in this way. Okay, and that's some asymptotic behavior. Now you could tell me where you started with this Integro-Differential Painlevé 2, but now we are showing to us KDV. That's true, but this is how we discovered this stuff. So we were looking for this Integro-Differential Painlevé 2 equation, and actually we ended up with KDV, which was quite funny for us. But then we realized that the Integro-Differential Painlevé 2 equation is hidden in this slide. Okay, why? Because you have this Schrödinger equation, but also you have that here the potential can be written explicitly in terms of the eigenfunction. And so what you can do, and this is just a simple corollary, from the Schrödinger equation and this additional equation that we proved, you put the second equation in the first one, and you immediately get an integral differential equation for phi, which is this integral differential equation that I showed to you. Okay. And this integral differential equation, if you come back to the original variable s and big T, well, you will find exactly the same equation written by Amir, Kovin, and Kastel. Okay, but this equation for us now, it's integrable, but in the sense that is an equation for an eigenfunction of an integrable system. Okay, so it's not obtained through the usual lax pair, but more about studying information about the eigenfunction. Okay, and actually this result extends to the case of general weight. So in order to study application, we started with the Fermi weight. So this function sigma of z equal to 1 divided by 1 plus exponential of minus z. But actually, this result, they hold for general weight sigma, also with discontinuities. And so what you get is a whole family, we believe, new family of unbounded solution of KdV. Why unbounded? Well, because you have this term x over 2t, and this suggests that indeed, when t goes to 0, something bad happens. Okay, and an exciting thing to be studied, and something that we studied with Giulio and Tom, with Giulio Woods and Tom Clays, is the singular behavior of the function uxt when t goes to 0. Okay, and I don't have time to explain all the details, but essentially you have different behaviors studying how you go for t equal to 0, how you move also x. So if x is positive, actually you have that the initial data for t equal to 0 is well defined. But the one for x negative, no, is singular, because, well, it goes like x over 2t plus exponential terms. Okay, so you have on one side singular behavior, on the other side you have regular behavior, and then in the middle you have something which is in between, and it's given actually by self-similar solution to Painlevé-2. So this solution that we wrote here, where y gamma is the asymmetric solution of Painlevé-2. Okay, so you have sort of phase transition, and actually this phase transition that can be interesting for KdV, they're actually very interesting also in the theory of the Kaldar-Parisi-Zhang equations, because they give you large deviations for the narrow wedge solution. So solution of the Kaldar-Parisi-Zhang equational distribution. And one important thing is to study the large deviations of this distribution. And it turns out that these large deviations are described by the asymptotics of the corresponding KdV equation. Okay. Antonio, how much time do I have? Not much, right?
I need to ask you to wrap up, if possible.
Yes. Okay. So I think that I will just basically finish here. So I just described to you the first approach. Just if you're curious about that, there is another approach that we introduced with Thomas Botten and Sofia Taricone. I will not give you details, but the interesting thing is that instead of studying just this QST that we defined before, you can study a whole family of kernels that depends on an additional parameter n. Okay, and well, everybody knows here, I believe, that Painlevé-2 equation is a self-similar reduction of modified KdV. In this setting that we studied with Sofia Taricone, which is my student, and Thomas Bottner, what we found is an integral differential version of the modified KdV hierarchy, and then these freedom determinant that we define here are given in terms of self-similar reduction of this integral differential modified KdV hierarchy, which is a new integral differential Painlevé-2 hierarchy that we studied, that has many interesting properties. And if you're interested about it, well, I invite to read the paper. Okay, thank you very much. I finished.
Thanks very much, Mattia, for a very interesting talk. So we're open for questions. Is there any question?
I've got a question, if I may.
Hi, Peter.
So a nice talk, Mattia, and good to
Thank
see you. Very interesting stuff, and I was happy to see Tom's talk yesterday. So now now it's making a little sense. Yeah, thank you. So I like this formula for the solution, this KDV solution written in terms of the integral of squares of the Schrodinger solutions, and I wonder. What I was wondering is if, yeah, that one right there. And I was wondering if there's any, if you can see any connection with, I mean, you know, there's some stuff that's known about expanding functions and squared operator. And I'm wondering if that's like this connected to this work of Sachs from the 1980s. Probably different boundary conditions, but I'm wondering if there's some connection.
I do not know, but I have to tell you that when we found this equation with Tom, we were wondering, we thought, well, this should be known in some way or something similar, and we were not able to find references. So if you can give me some references, I think that it would be very useful for us.
Okay, I'll type something in the chat for you right now.
Thank you very much. Because when we
sure.
saw this equation, we thought, okay, this should be known in some way or something similar at least, but we didn't find anything. So,
any more questions?
Peter, question to Peter. This is Alex. Peter, you mean square eigenfunctions like in finite gap solutions? That's what you mean?
Like yeah, I mean, just generally the squared eigenfunctions of the Lax operator solve the linearized equation usually, right?
Yeah,
that's yeah. So here there's a integral of squared eigenfunctions of the Schrodinger operator with potential v that solve the nonlinear problem. That's what I'm saying. But you know, but the completeness of the squared eigenfunctions is like an independent fact. It's something that happens like for each fixed t or something like that.
what I found, I mean, I found some similarities with some articles by Zabrodin and Zotov, in which they prove that if you have Lax pair for Painlevé equations, then the eigenfunction satisfies a quantized version of Painlevé, in the sense that you take the Hamiltonian of Painlevé, you quantize this, and the eigenfunction satisfies the quantized version. It's something similar here, but I don't know if it's really related or it's just by chance. I don't know. Thank you for the.
Something, we have a reference from Peter.
Thank you very much, Peter.
And, any more questions? If not, I've got a question myself. So, Mattia, in the context of random matrix models, what happens in several examples is that you have the partition function, and this happens to be the tau function of an integrable system. So it could be KDV or total lattice, whatever. And then the solution, the partition function of the model is specified by a particular solution of this integrable system. And this is specified typically by the initial condition. In your case, so the initial condition is ruled out because when t goes to 0, it's not clear what happens. So how you characterize, if I understand correctly, you characterize the solution via the boundary conditions.
That's not at infinity, yes.
Okay.
A little bit like when you do with asymmetrical solution. You say, well, it's the only solution that decays exponentially at infinity, and this is at the plus infinity, and this is the same. But so another thing that I can tell you, because I think that, well, this speaks to you, is that so in a way you have that, because as I said before, you have that V is a solution of KDV, but also X over 2t is a solution. So this freedom determinant, in a way, is a ratio of two solutions of KDV. I mean, a ratio of two tau function. Okay, and this is something that was interesting for me because with Adel and Van Merbeke, we had something similar when we were studying Tracy-Widom distribution. So in a way, it seems to me that this is the way to think about it. These freedom determinants that are gap probability, they're not partition function, they are ratios of two tau functions for KDV, And this makes sense because actually, at least in the finite n case, you can write a gap probability, for instance, for GUE as a ratio of two partition functions. So in a way, this is the infinite dimensional generalization of this idea, in a way.
Okay, so yeah, this is very interesting indeed. So you look at the sequence of the tau functions, and the ratio determines the solution.
It seems to me that something similar here happened, but yeah, but it's not really. I mean, I'm not stating any theorem, but the idea is this is the way I think about it.
That's really cool.
Thank you.
Any more questions? Okay.
Yes, I have a question. So can you explain the Riemann data to define the link of the KPZ equation in the Riemann data in the jump to define the Riemann-Hilbert pattern?
So in the jump, you have sigma, this and this. Sorry. So I go to the Riemann-Hilbert problem.
The function, the Riemann-Hilbert pattern, you define the eigenfunction, right? You have the
yes, that's correct. That's correct.
So can you explain the connection to the KPZ equation in the Riemann in the jump?
The connection of KPZ in the jump?
Because the jump does not reflect. Okay, I don't understand why the Riemann the jump has some connection to the QXT. So
to KPZ, you mean?
Yes, yes.
No, this is a very interesting question, but I don't understand it either. I mean, I don't understand in the first place what KDV should.
Okay, the proposition tells us that QXT is linked to the eigenfunction, right?
That's correct. That's correct.
So but that means the jump must reflect some property from the KPZ equation, right?
It should, but this question, because actually we are not the only one observing that this KPZ is related to KDV and then KPZ. There is an article by Castel and Remenick, but as they say, and I agree with them, we don't see any reason why the physics of KDV should appear here. I mean, who knows why KDV or KP is here? This is not very clear. The only reason that makes sense is that you have random determinants. And you know, since the work of Sattinger and Pop, that when you have random determinant of a special type, you have solution of KB. But this is mathematical explanation. Physically, why do you have that? I have no idea. But this thing of the jumps that you're saying, and this will be the last thing that I will say. Sorry to steal your time. This jump here tells you that since you have this sigma here that depends on Z, it means that here you don't have isomonodromic deformation anymore. Okay, so basically, when you study this extension in the integro-differential realm, at least in this setting, you lose this isomonodromic property. Okay, if you want to study isomonodromic Lax systems related to this integro-differential Painlevé 2, well, you have to admit operator-valued Lax pairs, and this is what we did with Thomas Botten and Sofia Tarico.
Mattia, I will think that here the sigma Z represents some scattering data of KPZ.
Of KDV, yes, this is how we thought about it. It's a kind of generalization of scattering data. Yeah, you're right. This is absolutely correct. Yes. Generalized scattering data, let's say. Yeah.
Okay. Okay. Thanks very much. So we have time for some open discussion, but I would like to take a chance to thank all today's speakers, and so I'll stop the recording and we can have an open discussion for